I guess we are ready. Hi. Um, so yeah, we are continuing with our meta-analysis interpretation, I would say, and description of what are the sections involved represented in a meta-analysis in a forest plot. So yeah, I'm recording in Loom. Uh, just to give you a description. Now going back where we stopped previously. So yeah, we were not able to convert digits. Let me rerun it. Error method. As far as I remember, we were not able to convert this digit of the standard deviation into two. After decimal, only just two digits. And one more thing we were not able to do is uh, we were not able to write favors intervention over here or below this plot. Let me put it in a comment format. Hashtag, hashtag. Yeah, the feature what it is in Art Studio is that if you're going to put hashtag before it, will and R will not run it. It will just consider it as a text. Okay, let me run this thing for plot and then we will be having understanding what all things we are missing and then we will put all the things together. First, we need to change the study. This SMD is perfect, 95 okay, weight okay, random effect yeah. And now we need to put something over here and we need to color these things. Okay, great. So, post that, let me put this red lag, G dollar, then G X. So why am I putting X? The reason is that we have named the study as X. I guess yeah, X equal to read Excel for meta-analysis. So this Excel file has been written as X in this. So we need to put X. That is X authors, comma Paul dot assignment. Let us make it blue. Then Paul dot let's put square lines, yellow, and one more thing. Paul dot leave it. You can explore. There are a lot of options to color it. Yeah, two more things we need to do. One we have done with the stud lab authors, and now we need to put two digits after the decimal. As you can see, there are four digits after the decimal. For this SD, we need to convert it into two. So we need to write digits dot SD equal to okay, yeah, it was labeled. So it could be lab.p and label.p. So what we're gonna do, we're going to put label, we're gonna name it. It was written experimental over here, so we're gonna name the experimental arm as Atorvester. So we need to put this in inverted comma, double inverted comma. And label dot what was the controller? That was standard. So let me get this is underline as as now I need to put. favors intervention. Okay. Now let us put both things in that case. Favors intervention, comma, label dot left, favors control. Okay, so I guess we will be getting something favors intervention on the right hand side and favors control on the left hand side. Let's see. Let's run it. It seems okay. Let's zoom it. And yeah, we do have all the things study, all the description of the study name and all with study names. We did colored the diamond, and the thing is not reported over here whether it's stable control or intervention. So as we can see, hypothetically, our study favors the intervention, which improves HDL level, high density lipoprotein. Now I've renamed this experimental arm as Torvastatin and control arm as standard of care. We have reduced the decimals after the once we have reduced the digits after decimal for this standard deviation, which we were not able to do in the earlier video. So yeah, now what we're going to do is that we are going to understand what are the elements reported in this forest plot. So yeah, that would be it. So you need to watch it in the continuation with the previous one, then only it will be helpful. But to give you a short description, we added three things which are highlighted over here. So these were the three things which were new, which we were not able to do in the previous video, which is reducing the number of digits after the decimal, giving labels, uh, and reporting whether it favors the intervention or favors control below this forest plot is in the forest plot itself. One more thing I would like to say is that we can also run summary to get all the details in written format, not in this pictorial format. It is way too similar what is reported over here. Just the uh, graphical representation is not good, as you can see. So there are few elements which are provided over here, which is missing in this figure. We will be dwelling into that also, and we will be discussing how other sections are important when we are actually viewing a forest plot, and what are the things that should come into your mind when you are actually looking into a forest plot and interpreting it. So going straight to the presentation. Okay, so let me start with the start. So yeah, this presentation is very short. It's not a very deep understanding of a forest plot, but it's more on what are the different sections provided in the forest plot. And when you see a forest plot, you should be able to understand these other sections which I should be focusing on, and at least I should have a brief idea about those points. It's not much of a statistical thing. Not no any formulas are there. It's just a basic description. Uh, it is having the digits. Well, why didn't change this intervention into a conversation when I copy pasted it over here? So, what are the sections which we are going to see into this forest plots are like this? For this study, second will be the intervention comparator. Third will be this entire section of standard mean difference. Uh, it is reported in pictorial form over here, and then this values and the 95 confidence interval, followed by this weightage, and what are the different models, what is random effect model, what is common or fixed effect model, and how to check the heterogeneity. First thing first, yeah, these are the certain missing sections which are highlighted as a bold values, which is Z, which was not reported in the forest plot, the P value for the random effect model, the H value for heterogeneity, and the Q value, which is chi-square for this heterogeneity. It was not reported in the forest plot. So usually this value and this values are reported over in most of the forest plot, but I'm not sure why it is not reported in this. Uh, if it's not reported, it's fine, but if it's reported, you should be having an idea what does this mean. So going back to it, the first section which was highlighted in the circular form, that is study title. So the usual format which has been used in naming the study in a meta-analysis is first author surname. Then obviously followed by ital. If usually a meta-analysis is conducted by at least two or more than two people, so you will have to write ital followed by the first author surname. Then usually it is followed by year. Well, what problem arises is that what if the first author surname is same and even the years are same? I will try to put this presentation in this in the YouTube video so that you can go through it. These are the two study which I was working on along with my colleagues. It was having same author name, initial author name, and the year of publication. So what we did is we used references to differentiate it. Means obviously the references cannot be same. So we used square bracket and we put 16 over there or 17 over there so that it should be differentiated. That's how usually people work with the same author and same year of publication. Now, what was the square thing which was reported over there? It consists of sample size, mean, and standard difference. Well, what does sample size mean? It's a simple number of peoples or number of patients which enrolled into the RCT or any studies for sake of observation. Usually, in most of the meta-analysis, the sample size after the study has been completed or post-study or post-intervention sample size has usually been taken, followed by mean. Now, you can take usually what happened in some of the meta-analysis, the authors prefer to take the mean after all the intervention of the all the studies have been conducted. For example, at baseline, the HDL value may be 25, which is low actually, it's not good. And post intervention, it came up to be 42, which is above the minimum requirement of good HDL level. So what few of the authors will do, they will only take the post intervention HDL level. Well, some authors, what they do, they take a difference of pre and post. So it depends on your methodology, what method you are going to follow. Similarly, the standard deviation, the author will take the post intervention standard deviation, or the author will take the difference of the standard deviation. That is pre minus post, or post minus pre, depending on the author's methodology, whatever he or she is following. But what happens in most of the time when I was doing my first systematic review and meta-analysis, we did have some 30 odd papers, but all the papers were not reporting standard deviation or standard error. They were reporting either standard deviation or standard error. So both are not same. Now what are we gonna do? We cannot compare standard deviation with standard error. We have to convert either all the standard error into standard deviation or all the standard deviation into standard error. So this is the Cochrane book chapter where you can find methods of converting standard deviation to standard error and vice versa. So it's needed. You cannot make a comparison of standard deviation with standard error. Similarly, I would like to share one more thing when you are actually conducting meta-analysis with continuous variable. For example, if you are taking IL-6 level, interleukin 6 level, some of the authors might be reporting it as mg per dl, or some of the authors might be reporting it as maybe gram per liter. So you cannot compare mg per dl with gram per liter. You have to convert in either into mg or mg per dl all the outcomes which have been reported, or into gram per liter. That this is the basics thing which we need to take care of, because once you have done with all the things, you have written the report and you are planning to submit to a journal, there will be a reward back from the editors or from the reviewers who are going to check your paper, that you have made a meta-analysis with such a serious flaw that you have not converted your values into a single into a format which is common across all the studies. Now, what are the outcomes and and their analysis method? This is something which really takes a bit of a time in understanding, because if you're already aware of it, it's pretty fine. But most of the time, it creates an issue of the basic understanding of how whether to use a mean difference or odds ratio, risk ratio, hazard ratio. So yeah, let's come to that topic first. For example, recently we were working on a project in which we initially planned to go with biomarkers, which are continuous outcome, and then we find out that okay, there are not many biomarkers reported in the study, or if the biomarkers are reported, it is not consistent across the different studies. So we decided not to take the biomarkers as an outcome of interest, and we decided to take COVID-19 positivity, that is RT-PCR positive report. Along with that, we took SCRU, that is healthcare resource utilization, and we took adverse event as an outcome of interest. So let me tell you all the three outcomes, that is uh, number of patients which turned out to be COVID-19 positive, number of patients who had adverse event following COVID-19 positivity, and then number of patients who used healthcare resources during COVID-19 positive. This all comes under dichotomous outcome. So we thought and come up with an idea. Okay, let us take odds ratio for the comparison. But in one of my previous study, for the first study, we took the biomarkers and we compare its efficacy on COVID-19. So over there, as biomarkers are continuous outcomes, so we used standard mean difference to compare the outcomes, or to actually the effect size was reported in terms of standard mean difference. So yeah, these are the basic things you should be aware of, whether your outcomes are in continuous format or in dichotomous format. Following that, you can either use mean difference, standard mean difference, odds ratio, risk ratio, and hazard ratio. Following that, you can decide whether to go with which of the format of reporting the study. Now, one more section with there, and I've merged all this thing, that is weightage, study effect, and how to check heterogeneity. Now, why it is important to understand the weightage criteria? Why is it actually necessary that we should have a weightage? Well, what weightage actually signifies is that which study is giving extra importance in your meta-analysis, or when you are conducting a meta-analysis, you might be having a minimum of two study and maybe four or five studies. Suppose, for example, let us have three studies in your meta-analysis. One is having a sample size of 20, one is having a sample size of 100, and another one is having a sample size of 200. In the first study, which is of 20, it is showing a positive effect. Second one is showing a neutral effect, and the third one is showing a negative effect. Well, obviously when you are going to run the meta-analysis, there is a good possibility that the effect size may be neutral, or there may not be any statistically significant positive effect of your intervention. Why? You would be asking, when the 20 study number of patients is having 20 is showing so good efficacy, why we cannot go ahead with that? Why my meta-analysis still is showing a result which is not statistically significant and is not favoring the intervention? That is where the weightage thing comes in, because your RCT of 20 studies low weightage when compared to that of 200 sample size study. Usually, there are two ways of providing weightage. One is in random effect model and one is fixed effect model. In random effect model, this sample size things came come into place. The study with higher sample size gets more weightage compared to that of lower sample size. And in case of fixed effect model, the weightage is usually provided equally to all the studies. There is not major deviation in weightage in providing the weightage to the study. Now, how the weightage is being provided, it is inversely proportional to variance. Means lower your variance of the study, higher will the weightage given to that study. Now, what are the effect sizes? As I was earlier mentioning, that there are two effect sizes usually, that is random effect model and one is fixed effect model. Well, what fixed effect model signifies is that there is very less heterogeneity between your different studies, which means your study A, B, C, D, E, and F are very similar to each other in terms of inclusion criteria, in terms of exclusion criteria, in terms of other factors like they have selected same patients. The demography of the patients are very similar. The clinical characteristics of patients are very similar. So if in such case we are very confirmed that all the five or six studies are very similar to each other, then the fixed effect or the common effect models comes into play. But if there is a high heterogeneity between the different studies, or the studies are a bit different from each other, in such case scenario you have to use a random effect model. So this is the basic difference why and when we are supposed to take random effect model and a fixed effect model. Now, how to test whether the heterogeneity is high or not? So there are a few methods of checking it. First is I square, tau square. It's not H index. It is just H score. So let me correct it. That would be great. It's H. So yeah, it is H score and then it is chi square. So I square, tau square, I square usually range between 0 to 1. 0 represent means negligible heterogeneity, whereas 1 represent very high heterogeneity. Similarly, tau square is also reporting heterogeneity. Now, what is the difference between I square and tau square? The basic difference is, I'm not going to go into statistics thing, but the basic difference is I square is reporting heterogeneity between study, whereas tau square is reporting heterogeneity within the study. So there is something H score also which gives information about heterogeneity, and then there is a chi-square which is actually used to check whether the heterogeneity is significant or not. For example, if your tau square is reporting 14, maybe 20, 30, 40 tau square I'm saying. So how can I say whether this 20, 30, 40, or maybe 50 is actually significant? That is reported by through this chi-square. So if the chi-square values or the p-value is less than 0.05, I can say with statistical surety that the heterogeneity within this study is significant. Means your studies are quite different from each other. So that's how we are going to check for heterogeneity. So let us go back to their first plot. So we did cover all the sections over here. We checked how to report a study. We checked how to check for this intervention comparator. What does this total sample size, total mean for each study? What does this mean? What are the standard deviation? Uh, how the author can report mean in two ways, either the post-intervention mean or the difference between the pre and post mean. Similarly, the study could report standard deviation or the standard error. So you either need to convert standard deviation into error or error into standard deviation, but it should be consistent across the study. Similarly, we understood this standardized mean difference. Through this, I can say, okay, the outcome was at least continuous outcome. And then the interpretations are also very simple. That I can say the intervention, which is atorvastatin, improves HDL level by 5.15 maybe uh, nano. maybe milligram per liter, compared to that of standard of care, which is statistically significant. Now weightage, we also checked how the study is given weightage. It is usually based on two format, that is fixed effect or random effect, and weightage is inversely proportional to variance. So higher the variance, lower the weightage. Lower the variance, higher the weightage. Similarly, we check for this random effect model and common effect model, how does this two comes into play, and it depends on the heterogeneity of the study. If the heterogeneity is high, or there is the studies are very different from each other, then we need to use random effect model. If the studies are a bit similar or are similar to each other, then we can use fixed effect or common effect model. Now then, next we checked for this heterogeneity. We understood what this I square and tau square. What are the basic difference between I square and tau square? And then we came to know that okay, even if the I square is reporting 99%, whether this is statistically significant or not, it could be checked through the chi-square test. Now, the things which we missed in this forest plot are this section. What is the Z value and then what is the P value? Well, Z value is normally not reported in meta-analysis plot, but this Z value actually represents how much your standard deviation varies in your sample size. So it's not of that deep interest. I've hardly seen any meta-analysis plot reporting Z value. Obviously, I can be wrong. It could be of high importance, but yeah, you should be knowing what this jet value is and what is this p value. It reports whether this standard mean difference which we acquired over here is significant or not. So yeah, it is significant because it is less than 0.05. You could have also said that after looking into 95 confidence interval, suppose the SMD is 5.1455 and then the confidence interval is from 1.728. So one doesn't come in between of that, so it means that it is statistically significant. Similarly, we're talking about H score over here. So it also reports whether the study is having heterogeneity or not. As that of Z square, I have not seen much of the study reporting H value to quantify the heterogeneity. It's mostly the tau square or the I square which has been reported, and the Q, that is chi square. So over here the chi square is significant, very significant. Then this 5 is actually degree of freedom, which means the study is actually heterogeneous and it is statistically significant. We need to interpret it in such a way, because even if it is showing that the atorvastatin is improving the HDL level by 5.1455 maybe milligram per DL, but it should be interpreted with a caution that the heterogeneity between studies were high. So yeah, we need to report this sections also when we are reporting the results of meta-analysis along with the final effect. You have to report whether the heterogeneity was high or not, and if it was high, whether it was significant or not. So yeah, that are the sections which you need to have a basic idea about it when you are actually looking into a forest plot. And this topic, this discussion didn't cover any portion of statistics, I would say, with any formulas in it, because that was not the priority of this discussion which we have. But yes, definitely we will be discussing all the things, all the statistical things which are at least needed in this health economics and outcome research domain. But that will be happening a bit later. First, we will be learning the forest plot, that is meta-analysis, which I guess by now you should be able to run it. Second, we will be learning about meta regression. Third, we will be learning about network meta analysis. And then we will be dwelling a deep understanding into the statistics which are usually needed when you want to pursue a career into health economics and outcome research, or if you want to work in literature or maybe publication of systematic review and meta-analysis, or even with network meta-analysis. That's what I've thought about of this continuation of the video. So thank you so much. If you have any doubt, please feel free to mail me or write in the YouTube video comment section.